Okay, today we're talking about Chapter 7, Section 6, Polynomial and Rational Inequalities. So we're going to be looking at inequalities, and inequalities obviously are going to be equations that are not equal. They're going to be equations that are in the form of less than, greater than, and of course, or equal to's. Greater than or equal to, or less than or equal to. So let's go ahead and snip this first. Just a nice little introduction to the section. But we like to jump straight to examples. Examples are pretty good. Not much introduction is needed in our examples. So use the graph of so this is actually pretty easy. I probably shouldn't have snipped that. I should have kept it as looking at the graph. And we'll just go ahead and put the solution here too. Okay, so this is the easy way to solve it. If you have nice, neat numbers that aren't fractions or decimals or anything like that. So we'll just go ahead and snip this and talk about it. So it says use the graph to solve the inequality. So so we have the equation x squared minus 6x plus 5 is less than 0. So if you graphed it, okay, so where is this graph less than 0? And of course, when we say less than 0, we're talking about the x-axis. Okay, so where is it less than 0 on the x-axis? Looking at the x-axis, where are we under the x-axis? Okay, well, it's less than 0. It looks like from 1 to 5. Okay, not including 1 and not including 5 because, well, those are exactly on that x-axis. Where are we greater than 0? Well, we're greater than 0 everywhere above it, right? So again, look at this. This is our graph, the black line here. Where are we above that x-axis? Well, we're above it everywhere from, it looks like from 1 all the way down to negative infinity, right? And it looks like from positive 5 all the way up to infinity. Okay, so that's how we would write, well, I guess I didn't say that for A. For A, we said we're between 1 and 5, not including 1 and not including 5. And set Euler notation, it looks like this. And in interval notation, it looks like this. And then, of course, B would be kind of similar. We are above the x-axis everywhere that is less than 1, and we are above 0 everywhere that is greater than 5. Of course, in set Euler notation, it's written like this, and in interval notation, it's written like this. All right, so I definitely 100% hand wave through that, and that's part of it, right? We're supposed to look at the graph, and there's not really much I can write down or say, but I'll earn my pay with example 2. Okay, so we're gonna have to get boundaries and all that stuff, and you've probably seen or done this before, but I bet you haven't used it since and you forgot. So let's go ahead and jump into the example and figure this out. Okay, so let's just say you don't have a handy dandy calculator to be able to look at this, and we want to figure out, okay, so where do these what is the solution to this inequality, right? So it's an inequality. We have the less than 12 there, less than 12 right here. Okay, so we have the inequality. So we can't just simply, set it equal to 0 and then solve for x, right? Except we kind of can, right? We kind of can. And in fact, that is going to be the first step. Okay, so the first step is going to be setting it equal to 0. So let's go ahead and do 2x squared plus 5x minus 12 is equal to 0. Okay, so the first thing I did was indeed, I subtracted 12 from both sides, and then I set it equal to 0. Okay, and then from here we're going to go ahead and factor. So this factors into a 2x minus 3 and an 2x minus 3 and an x plus 4 is equal to 0. And therefore we see that we have x is equal to a positive 3/2 and x is equal to a negative 4. All right, well, I said negative, I just didn't write it, negative 4. Okay. All right, now this is where solving equations differs from inequalities. So what we're going to have to do here is we're going to have to make us a number line and have and make boundary points. And of course, all these are kind of laid out here in our steps. But as I've said before, I mean, we learn better by doing, so I'm doing. Okay, so I'm going to make us a number line real quick. And let's go ahead and kind of mark that off so we don't confuse anything. All right, so I'm gonna make boundary lines at these 2 points, 3/2 and -4. And of course, this is a number line, so we're gonna have a negative infinity and a positive infinity. So we're obviously reading this left to right from negative to positive, right? So we're gonna have a -4 here, and we're gonna have a 3/2 here, positive 3/2 here. Now here's the thing, and well, I'll show you what the textbook does, and I mean, there's nothing wrong with it, but so the textbook goes ahead and marks off all these -6, -5, -3, -3, -2, -1, all these points, okay? But you don't necessarily need to write all of them. You basically just have to write your boundary points, and as long as you just kind of know what you're doing, what you're looking at, you don't have to write -3, -2, -1, 0, 1, 3/2, and so forth, because it really doesn't matter. The big point is having these boundary points and knowing what numbers lie in between them. Okay. Well, so we have our boundary points, and what I'm going to do is I'm going to kind of mark off what the intervals are, okay? Because it's very important what these intervals are. So the interval over here is from negative infinity to a -4. This interval is from a -4 to a positive 3/2, right, or 1.5. And then this interval is from a positive 3/2 to infinity. Okay, so we marked off our intervals, and it's very important we do this because my solution to this equation is going to be some form of these 3 intervals. We don't know just yet, but it's going to be some form of these 3 intervals. So in order to figure out what the interval actually is, we're going to have to figure out a test point. Okay, now a test point is going to be within the interval. And I would always choose the smallest, like the absolute value of the smallest number. All right, what I mean by that is we have negative infinity, -4. Okay, I can choose, if I wanted to, I can choose -1077. Okay, but the thing is, what I'm doing here is I'm taking this number and plugging it into my original inequality and seeing if it's a true statement or a false statement. And I'm not in a hurry to square -1077. Okay, so I'm going to choose the smallest number I can, which would be -5. Okay, and some other pro tips we have here is if you have 0 available to you, always use it, always. All right, and in this particular interval, 0 is indeed in there. We're going to use 0. And then from 3/2 to infinity, well, 3/2 again is 1.5. So I'm just going to use a test point of 2 right here. Okay. So again, these are all the numbers that are in the interval. So again, like -5 is right here. 0, 4, 3, 2. 0 would probably be somewhere like right here, and then 2 would be about right here. Okay. And again, you don't have to actually write those, as long as you have a very good understanding of what the number line is. So anyways, we're going to go ahead and now take these test points and we're going to plug it into the equation. Okay, so let's go ahead and kind of get this set up. We're going to have a 2, and then we're going to put a squared here, plus 5 times that number is less than 12. Okay, so let's go ahead and start with a -5. Now we're probably going to be doing some mental math here, so try to keep up. If you can't, hit rewind. All right, so -5 squared is 25. 2 times 25 is 50, so we have a 50 here. 50 plus 5 times a -5 is a -25, so 50 minus 25. Well, 50 minus 25 is going to be equal to 25, and is 25 less than 12? No, 25 is greater than 12. So that means this is going to be a false statement. Okay, so we're going to put, so since it's a false statement, this will not be a solution. Okay, next let's put a 0 in here, and zeros are so easy to play with. That's why you always use them, right? Well, 0 squared 0, 2 times 0 is 0, plus 5 times 0 is 0. Is 0 less than 12? Yes, 0 is indeed less than 12, so this is a good interval. And then 2, right? Well, 2 squared is 4, 4 times 2 is 8, 8 plus 5 times 2 is 10, 8 plus 10 is 18, 18 is not less than 12, so this is a false statement. Okay, so with that said, what is my solution here? All right, well, my solution is only going to be that middle interval, okay? And we can write this in one of two ways. We can write this in interval notation, which would be just simply rewriting this, right? It's going to be -4 to 3 halves, okay? Or if I want to put this in set builder notation, we know that we can say this as x such that x is going to be between -4 and 3 halves. Okay, and let's go ahead and mark this off because it's getting a little, there we go. And that's it. I know that seemed kind of ridiculous, but that really is that's it. You just set things. You set the equation equals 0, and you find out what your zeros are. Your zeros are going to be your test points. You put your test points on a number line. I'm sorry. Yeah, I'm sorry. You put your zeros on a number line, and then you get test points inside those intervals. And then if it's a true statement, it's a solution. If it's a false statement, then it's not. And so let's do another example here. All right, this problem looks a little ridiculous, but it's actually pretty easy. Well, the getting the zeros is pretty easy, right? Because it's already in factored form for us. Okay, so if it's already in factored form, um, there's not much we can really do here. Well, I don't say much we can do. We don't have to actually factor the equation. It's already in factored form. So it already has my zeros at, it looks like it's going to be, we have zeros at x is equal to 0 and x is equal to plus or minus 4. So let's go ahead and put up our number line here. We know this side's infinity. We know this side is negative infinity. Okay. And so we know that we can go ahead and put 0 right here in the middle. We know that positive 4 is right here. And we know that negative 4 is right here. Okay. And again, you don't have to write all the other stuff as long as when you build the number line, it's what you expect. Okay. So we have 4 intervals here. This interval over here is from negative infinity to a -4. This interval is from a -4 to 0. This interval is from 0 to a +4, and this interval is from 4 to infinity. Okay, and now I'm going to get a test point in those intervals. So my test point here is going to be -5. Unfortunately, 0 can't be used. Well, the next best number is going to be 1s, positives and negative ones, because I'd much rather square 1s and negative 1s than other numbers, right? So the interval here, or I'm sorry, the test point here is going to be -1. Test point here is going to be +1. This test point here is going to be +5. So again, what we're going to do is we're going to plug these values into our equation up here. Okay. Now, there's when we have an inequality, dealing with a 0, greater than 0 or less than 0, it's kind of well, it is easier, and I'll tell you why. So let's go ahead and do this. Let's do x. Let's go and rewrite the equation. Okay, because we can pretty much, we know that a negative times a negative is a positive. We know that a positive times a negative is a we know that a positive times a negative is a negative. And so we can kind of use that thought process here. So what do I mean by that? Well, let's just we're going to plug in negative 5 in for x. Okay. Well, negative 5, that's a negative. Negative 5 plus 4 is a negative 1. Negative 1 squared is positive. And then we have a negative 5 minus 4, which is a negative 9, which is a negative. Okay, so what is a negative times a positive times a negative? Well, a negative times a positive is a negative, right? Negative times a positive is a negative. And then negative times a negative is a positive. And we're wanting values that are greater than or equal to 0. Well, of course, if it's positive, it's greater than or equal to 0. So the first interval works. Okay. Next, we'll do same thing with a negative 1. Okay, so negative 1 here, negative 1 here, negative 1 here. Okay, well, negative 1 is negative. Negative 1 plus 4 is a positive number, positive squared. This is always going to be positive, right? Because anything squared is always going to be positive. But we'll still do the kind of arithmetic in our head. And then we have a negative 1 minus 4 is a negative number. And we have the same thing. We have a negative, a positive, and a negative. A negative times a positive is a negative. A negative times a negative is going to be a positive. So the second interval also works. Okay. Excuse me. Using a 1, well, that'll make this a positive. And I said this is always a positive. And 1 minus 4 is a negative 3, which is a negative. Well, a positive times a positive is a positive. Right? Positive times positive is positive. And then a positive times a negative is a negative. So this tells me that this interval does not work. And then lastly, 5, well, that makes it a positive. This is always positive. 5 minus 4 is 1, which is positive. So it's a positive times a positive times a positive. So this tells me that this interval works. Okay. Well, we have our three intervals that work. So we can write our solution as in interval notation. Okay. So in interval notation, this is actually pretty. I won't say pretty obvious, but notice how these two intervals they work. So we can kind of combine those two intervals together. Okay. So we can say from negative infinity to 0. Okay, and we're going to include 0 because if you recall, you put the bracket there when you have an or equal to sign. An or equal to sign. Okay. All right. And then that is union with this interval here, which is 4 to infinity. And again, we include the number 4 because it is an or equal to 4 to infinity. And then, of course, my favorite, set builder notation, which is just going to basically write it out, right? So x such that x is less than or equal to 0, and we can write the word and x is greater than or equal to 4. Okay. All right. So this one was going to be some calculator work because it's trying to get the trying to get the x value. We have to use the quadratic formula. And instead of doing the quadratic formula behind the scenes, we're just going to go ahead and snip all this. And I forgot where I snipped it at the bottom of step 3. Okay. Alrighty. So again, it's the same thing. I just didn't want to. I don't like to do the calculator behind the work or behind the scenes. But same thing here. You take x squared plus x minus 4. We can't factor that, so we have to use the quadratic formula. And when we use the quadratic formula, we have the test points of -1 minus the square root of 17 over 2 and -1 plus the square root of 17 over 2. And then, of course, our test points we use, we figure out, we have negative 2.5, and a 1.5-ish. Where our test point here would use, a negative 3. All right, this is a nice fleshed out number line. This is a number line I haven't been using so far. Like I said, so far on my number lines, we just use the values. We don't fill in the blanks of everything in between, right? But I guess this is pretty good to show that you can if you want to. It's just to me, as I write things get a little cramped. But anyways, you have our zeros. You put in your test point. So in this particular case, looks like we use a negative 3. Use 0 always if it's available to you, and then a positive 2 probably. Okay, and of course that's exactly what the test points were here, and it's the exact same as examples 1 through 3. Again, a little hand wavy. I'm sorry. It's just again quadratic formula. I don't want to do it behind the scenes. But the next few examples, all right, I do have to actually explain, and so you'll actually see some computation from me. And we have fractions. Okay, now fractions make everything just so much more complicated, right? Well, again, don't be like me. Don't be like, well, hope there's one of these on the test, and not actually try, because it's actually pretty darn easy if you think about it, right? So let's go ahead and think about it. Well, we have the inequality 3 over x minus 1 is greater than 0. Okay, well, if I were to, solve this for 0, well, not solve for 0, but a test point here is going to be where the denominator is equal to 0. We know that we cannot divide by 0, so that's my only test point here, and it's just at positive 1. Okay, and we'll go ahead and mark off the number line here. And my only test point is here at positive 1. Right? So if positive 1 is my my test point, and again, that's because if I didn't make it clear enough already, there's nothing else here except for what makes that denominator equal to 0. There's nothing else to mess with. And where that denominator is equal to 0 is going to be a boundary point. Okay, well, we have the interval over here from negative infinity to a positive 1, and we have the interval here from 1 to infinity. So my test point here is obviously going to be 0. Love using 0. It's too easy. And then 2. Okay. Well, if I plug in a 0 into to this equation, okay, well, 3 over a negative 1 is going to be a negative number, and a negative number is not greater than 0. And if we plug in a 2, okay, well, 3 divided by 2 minus 1, which is 1, 3 over 1 is 3, and 3 is indeed greater than 0. And so that is my only interval that works. Okay, so again, in interval notation, we would write this as, okay, so this is not an or equal to, so we're just going to simply use 1. So 1 to infinity, and then my set Euler notation, which is x is greater than 1. Okay, and that's interesting. I think we have another typo in the textbook. This says the solution set is x such that x is equal to 1. Another typo in this textbook. It is not equal to 1. It is 1 to infinity, or as we wrote, this, x is greater than 1. That's unfortunate. We found a lot of typos here. Next semester, I'm going to have to keep track of all these. All right, so more fractions. The last fraction was pretty easy. This one is we're ramping up just a little bit. Okay, so how do we ramp this up a little bit? Well, we have to also account for the numerator now. Okay, because on the last example we had the only the denominator, and we just had to figure out what made the denominator equal to 0, and that was it. Okay, in this particular case, all right, so obviously one of the boundary points is going to be 4, okay, because that's what makes that denominator equal to 0. Now I have to deal with the numerator. Okay, so in order to do that, let's go ahead and do the arithmetic here. I'm going to go ahead and multiply x minus 4 on both sides. Okay, so we're going to put the equal sign here, x minus 4. And again, all I did was take this, multiply both sides by x minus 4. Uh, looking at this solving, I've got x plus 2 is equal to 3x minus 12. Solving here, it looks like we can subtract 2, add 12, so we've got 14 is equal to 2x, or in other words, we have x is equal to 7. Okay, so 4 and 7 are going to be my boundary points. Okay, and again, the 4 I just got because that's what makes the denominator equal to 0. The 7 because I got rid of the inequality, put an equal sign, and solved. So let's go ahead and make our number line. Okay. So again, we have the 4 and 7. So we don't have to necessarily start at 0. All right. Now I say this because some students I've seen they put 0 right in the middle, and then of course you go 1, 2, 3, 4. There's 4, 5, 6, 7. There's 7, and then you just kind of have this much a little bit to play with, right? And again, the whole point of why I do what I do is because it doesn't really matter how you draw it. There's 4 and 7, and it looks nice and neat on the eyeballs, right? Okay, so let's go ahead and get our intervals here. So we've got negative infinity to a positive 4, 4 to 7, and then 7 to infinity. Let's go and erase this, get that out of the way. All right, so negative infinity to 4, always use 0. Easy peasy. 4 to 7, I'm going to use the number 5. Smaller the better. 7 to infinity, well, 8's going to have to be the one. All right, and well, we just have to do the arithmetic now. Okay, so we're going to plug in and let's put this down here so we can really see what we're doing here. We'll put, let's see, we'll do x plus 2, x minus 4, so that's equal to 3. Okay, so I'm going to go ahead and erase the x's there so I can, kind of put the my test points in. So 0, 0. Okay, so 0 plus 2 is 2. 2 divided by negative 4 is a negative 1/2. Is negative 1/2 less than or equal to 3? Yes, it is. So this interval works. Okay. Next up, we have a 5. So 5 and 5. So 5 plus 2 is 7. And then 5 minus 4 is 1. We have 7 over 1. Is 7 less than or equal to 3? No, it is not. So this interval does not work. And then lastly, we have the 8. 8 plus 2 is 10. 8 minus 4 is 4. 10 fourths or 5 halves. Is 5 halves less than or equal to 3? Yes, it is. So this interval works. And if I put this in interval notation, my solution is negative infinity to a positive 4, and we use a bracket there, again, because we have an or equal to. Oh, no, I'm sorry. No, we don't actually use the 4, the bracket. Why don't we use the bracket there? Good question, Sherman. Because if we included the number 4, that means that we could put a 4 right here in the denominator, but that's literally the only number we can't use, right? So we have to put a parentheses there. However, on the other side, going from 7 to infinity, we can use a bracket because, again, in this particular case, it is an or equal to, so we use a bracket, and we're good to go. Yeah, sorry about that. That was a quick mistake. And then, in my favorite, set bill notation, x such that, well, what should x be? Well, it looks like x should be less than 4 and x be greater than or equal to positive 7. Okay, and that's it. And let's see if the textbook got it right this time. Yes, good. All right, and I think, yeah, this is the last one. This is the last one, but I'm going to go ahead and snip this entire problem because I feel like, I don't know, I feel like putting this all on multiple pages would be a bad idea. Instead, we'll do the old snip and talk. The old snip and talk. That's a good one. Alrighty, so these are, this says solving Okay, do we not have special cases? I thought there was a special case involved. Yeah, inequalities with special case solution sets. Right. So the solution to an inequality is often one or more intervals on the real number line. Sometimes, however, the solution to an inequality may be a single point on the number line, the empty set, or a set of all real numbers. So in this particular case, these solutions are going to be um, these are tricky. That's really all they are. It's kind of tricky to think about. So if we solve the inequality x squared plus 6x plus 9 is greater than or equal to 0, we you might go into autopilot mode and you would think, okay, so we solve, we get our zeros, we get our test points, so on and so forth. But if you just think about it, well, it's always going to be greater than or equal to 0, isn't it? Because x squared is going to be a positive number, plus 6x plus 9. Of course, we see here it is a perfect square, uh, and x plus 3, and in no way will this ever be less than 0 or equal to 0. Well, no, it can do 0, sorry. It can equal 0 negative 3. But at no point will it ever be less than 0. And so it's every single possible number will work. Okay. Well, B, kind of using the same thought process, but this says greater than, so B is different because it's just simply greater than 0. A is greater than or equal to 0. Well, if we're saying that this x squared plus 6x plus 9 is greater than 0, well, then the only place where it won't be a true statement is where it is exactly equal to 0. And it is exactly equal to 0 at negative 3. Okay, again, these are all the same. This is the same throughout. The only difference is obviously the inequalities. So in every case, they can factor into x plus 3 quantity squared. Well, where is x plus 3 quantity squared equal to 0? Well, it's equal to 0 when x is equal to negative 3. And of course, that's where we see that we do not have the solution. And of course, the solution set would be x such that x is not equal to negative 3, or negative infinity to negative 3 union with negative 3 to infinity. Okay, so kind of the same, I wouldn't say same process, but the same thought process here, though. Again, exact same equation, except it's less than or equal to 0. Okay, well, we know that it's never going to be less than 0, which, by the way, kind of tells you what d is going to be. It's never going to be less than 0 because, again, they all factor into this. So the only point where it's going to be true is where it's equal to 0. And it is only equal to 0 at negative 3. And then, of course, lastly, x squared plus 6x plus 9 is less than 0. As I mentioned, kind of gave that away. It's never going to be less than 0. Again, this is what it factors into. It will never, ever be less than 0. So the solution there is the empty set. I'm pretty sure that does conclude today's lecture. Yes, that concludes today's lecture.